Good morning, welcome to the Lionhearted Academy. This is Richard Time. We're continuing our trigonometry lesson. Today we're talking about our trigonometry lesson, lesson number 37. We have started talking about the fundamental identities, fundamental relations between trig functions last lesson. So this lesson we are going to continue talking about that. Specifically, we're going to look at some examples, look at some the ways to simplify trig expressions using the fundamental trig identities. So let's go ahead and get started with that. Alright, so first of all, let's go ahead and look at some examples. Okay, alright, let's say we have cosine theta. Okay, so how can we express cosine theta using in terms of sine theta? Okay, well, cosine theta in terms of sine theta, let's go ahead, I'm gonna go ahead and write this down. So example 1, express all functions in terms of sine theta. Okay, so we're going to look at every function we're going to try to express them in terms of sine theta. Okay, in terms of sine theta. Alright, so first of all, let's start with cosine theta. How do I express cosine theta using sine theta? Is there any relationship between cosine and sine? Well, remember there's something called Pythagorean identity. The Pythagorean identity is sine squared theta plus what? Cosine squared theta equal to 1. Okay, so this is the fundamental relations between sine and cosine. Always remember that sine squared theta plus cosine theta, sine squared theta plus cosine squared theta equal to 1. So if we want to express cosine theta in terms of sine theta, we have to solve this expression. We have to use this equation to solve for cosine. Alright, so to solve for cosine, I have to subtract sine squared theta from both sides. So cosine squared theta equal to 1 minus sine squared theta. Okay, so this is going to be an important expression as well. So what is cosine squared theta? Well, it is equal to 1 minus sine squared theta. But we want to find cosine, right? We want to find cosine, not cosine squared theta. So we have to take square root on both sides of the equations. And when you take square roots, you have two roots, plus minus square root of 1 minus sine squared theta. Alright, so this is what cosine squared theta, or cosine theta, is equal to in terms of sine theta. Okay, now where does the plus and minus come from? Well, it comes from taking the square root, because we always have two roots when we take square root. But it is also there because remember the signs. Remember the signs for each quadrant. Remember it's ASTC, the acronym ASTC. So when sine is positive, cosine could be. When sine is positive, when you plug in sine is positive, it could be in quadrant 1 or quadrant 2. So in any given sine theta, there could be two possibilities for cosine. One possibility is in quadrant 1, cosine would be positive. One possibility in quadrant 2, cosine could be negative. Therefore, given sine, cosine would be either positive or negative. Okay. Alright, what about tangent? How do I write tangent in terms of sine only? Well, tangent is equal to sine divided by cosine, right? Is that true? Yeah, tangent is sine divided by cosine. So that means I can go ahead and replace cosine with the expressions we already got for cosine in terms of sine. So tangent is equal to sine over plus minus square root of 1 minus sine squared theta. Again, there are two answers. One is positive, one is negative. Okay. Now, what about cotangent? Well, cotangent is cosine over sine, or it's actually equal to reciprocal of tangent. So in this case, it's just plus minus square root of 1 minus sine squared theta divided by sine theta. So I'm trying to express cotangent in terms of sine only. Right? What about secant of theta? Well, secant is 1 over cosine, right? 1 cosine theta, so it's 1 over plus minus square root of 1 minus sine square of theta. Okay, and cosecant theta is 1 over sine theta, so just 1 over sine theta. This is the simplest one that we can express using sine. So what we have done is we can express every other function using one of the given function, and it is actually not very difficult, but all we're using is just using the fundamental identities, okay? Fundamental relations, fundamental identities, okay? Alright, let's look at some other examples. Alright, let's take a look at this. Cosecant square phi minus cotangent square phi. Now, how do I express this using a single expression, a monomial expression? Well, what's the relationship between cosecant square and cotangent square? If you look at the Pythagorean theorem, I remember it looks like this: 1 plus cotangent square theta equal to cosecant square theta. Okay, so that means how do I get to cosecant square theta minus cotangent square theta? Well, if you subtract cotangent square theta on both sides, okay, you get this, right? Cosecant square theta minus cotangent square theta will be equal to 1. So this expression will be equal to 1. Cosecant square phi minus cotangent square phi will be equal to 1. There's a lot of variations. For Pythagorean theorem, so you have to understand that we have a Pythagorean identity, and you can always move things around. You can subtract cotangent, you can add cotangent. There are different ways you can manipulate this expression. This equation can be written in 3 different ways, actually. Okay, so those are the things. For example, another one, 1 minus sine square theta. Well, 1 minus sine square phi, as we have talked about already, because sine square phi plus cosine square phi equal to 1. So 1 minus sine square phi is equal to cosine square phi. Okay, again, this is a variation of the Pythagorean identity. So don't forget, there are different variations of Pythagorean identity. Let me show you another one. Secant square phi minus 1. Well, we know secant square phi is equal to 1 plus tangent square phi. So if I subtract secant square phi, if I do minus 1, let's see what will look like. Okay, so we know 1 plus tangent square theta is equal to secant square theta. Alright, so if I subtract 1 from both sides of the equation, on the left hand side I will have tangent square theta left. On the right hand side I have secant square theta minus 1, so that will give us tangent square theta, or tangent square phi in this case, because we're using angle phi here. Okay, so let's show you another example here. Now, what about this? Tangent theta, cotangent theta, or phi, plus sine square phi plus cosine square phi. Alright, it looks like there's a lot of things going on here, but let's take a look at what's going on. Tangent phi times cotangent phi. What's the relationship between tangent and cotangent? Well, they are reciprocals, are they? So cotangent is 1 over tangent. Okay, and sine square phi plus cosine square phi there's a Pythagorean identity that tells us sine square phi plus cosine square phi is equal to 1. So, and tangent times 1 over tangent, they cancel each other out, so it's 1 plus 1. So the final answer for this expression is simply 2. So basically we're dealing with some basic expressions, how to simplify trigonometric expressions just using the things that we have talked about. Alright, let's try another one. Cosine square phi times tangent square phi plus sine square phi times cotangent square phi. Okay. It doesn't seem like we have a lot of things to do here, but let's go ahead and try to rewrite everything. Let's see, cosine square and tangent square, they don't have any, they are not related using Pythagorean identity. But cosine and tangent, they are related, because tangent is what? Tangent is sine over cosine. Okay, and sine is related to cotangent because cotangent is cosine square phi divided by sine square phi. So now, as you can see, we have a fractional situation here, and the cosine phi squared phi and cosine squared phi cancels out because you're multiplying. Sine squared phi times this times cosine squared phi divided by sine squared phi. The sine squared phi cancels out. So we actually ended up with sine squared phi plus cosine squared phi, and then now we can use Pythagorean identity to say, okay, sine squared phi plus cosine squared phi is equal to 1 because of Pythagorean identity. So first we use the quotient identity. We write this as a quotient. This is usually a very good way to go ahead and get started. We write tangent as a quotient of sine over cosine, and then see if there's anything that can cancel out and help us to be able to simplify this expression. Okay. Alright, so now we're ready to look at another set of simplifications. So let's go ahead. Let's look at this. Cosine x plus sine x times tangent x. Okay, so let's see what we can do with this expression. How do we simplify this expression? There are several ways we can approach this, but generally speaking, we want to convert them into something that we can deal with. Now, sine times tangent, I don't remember anything to do with sine times tangent in our relationships, in our fundamental identities, but I remember tangent is written as sine over cosine. So this can help us combine terms a little bit. So we have cosine x on the first term, but sine times sine becomes sine square x over cosine x. Right, now we have a fraction because in order for us to add them, we have to add them in terms of fractions. And in order for us to add the two fractions, we have to have the same denominator. So the first fraction is cosine x over 1. The second fraction is sine square x over cosine x. So we need the denominator to be the same, to have the common denominator, which is 1 times cosine x, which is cosine x. So for the first fraction, I need to multiply by cosine x over cosine x in order for the denominator to be the same, right? Okay, so then it becomes cosine square x divided by cosine x plus sine square x divided by cosine x. Okay, so now the two fractions, they have the same denominator. Now we can combine them. So the numerator becomes cosine square x plus sine square x. The denominator remains cosine x. But you can see sine square x plus cosine square x is equal to 1. So that's by Pythagorean theorem. Pythagorean identity, and 1 over cosine x is equal to secant x because that's the reciprocal. Secant is the reciprocal of cosine. So we have successfully simplified this expression using the fundamental identities. Let's look at another example here. Alright, cotangent square x divided by 1 minus sine square x. Alright, so first of all, let's take a look at this. Is there anything that we can use to simplify right away? Well, I recognize 1 minus sine square x. That has to do with what? The Pythagorean identity. And then, because sine square x plus cosine square x is equal to 1, 1 minus sine square x is equal to cosine square x. Okay, so this becomes simply cotangent square x over cosine square x. Now, is there anything I can relate cotangent and cosine with? Well, I know cotangent is the reciprocal of tangent, or cotangent is simply cosine over sine. So cotangent square x is equal to cosine square x over sine square x divided by cosine square x. Now when you deal with complex fractions, okay, now we're going to be using a lot of fractions and complex fractions in this section. How do we deal with complex fractions? When you divide by a fraction, you multiply by its reciprocal. Okay, so you multiply by the reciprocal of cosine square x, which is 1 over cosine square x. Alright, and now you can see that cosine square x, they cancel each other out because they are in the position to cancel each other out. One is on the numerator, one is on the denominator. So we have 1 over sine square x. And 1 over sine square x is simply cosecant square x because that's the reciprocal of sine. Cosecant is the reciprocal of sine. Alright? Great. Let's try one more... We're doing a lot of examples today. cosecant x minus cotangent x divided by tangent x plus cotangent x. Okay. Alright, now on the first look, this one seems to be very weird because we don't know how do we write everything, how do we relate everything. Well, they are all related in such a way. There are several ways to deal with this, but cosecant is related to sine, is reciprocal of sine. Cotangent is reciprocal of tangent, or cosine over sine. Tangent is sine over cosine, and cotangent is sine over sine. So that's one way, is to rewrite everything using sine and cosine. So let's see what happens after we do that. So again, cosecant is 1 over sine, cotangent is cosine over sine, and tangent is sine over cosine, and cotangent is cosine over sine. So now we have two sets of complex fractions. Now let's look at the denominator and see what's going on here. The denominator here is sine and sine. So okay, the numerator has the expression in the numerator has a common denominator of sine, but the expression for the denominator has a common denominator of sine times cosine, cosine times sine. So what we can do is to get rid of both the denominators and on top and the bottom, we can multiply by the least common denominator, by multiply by cosine times sine, okay, over cosine times sine. That way we will be able to get rid of all the denominators. Okay, so let's see what happens. The cosine sine times 1 over sine is cosine. Cosine times sine times cosine over sine, so this becomes cosine squared x, but the sine cancels out. Cosine times sine over cosine, the cosine cancels out, becomes sine squared x, plus cosine times sine times cosine divided by sine, so it's cosine squared x, the sine cancels out. And the denominator, oh, I see something now, because the denominator is sine squared x plus cosine squared x is 1. So the final expression is just equal to cosine x minus cosine squared x divided by 1, so that we don't have to write that. Okay. Alright, so those are some examples that hopefully will help you get started. We can do a little bit more examples, and there are a lot of other practice problems on the textbook resource that we can use. I can show you that, and hopefully you'll be able to try to practice this. And we'll go ahead and continue our discussions on trigonometry identities in our next lesson. Thank you, and we'll see you in our next lesson.